Welcome back. Let's get going on Quaternary period. So now we are at the Quaternary, which is 2.58 million years ago to the present. And now we are seeing that the Earth's global temperature is cooling since the Eocene gradually over time. And now in the Quaternary we have a lot of up and down movement in our temperature, up to the Holocene, which was a fairly stable time, albeit pretty short in Earth's geologic history, up to where we are now. So what are all of these ups and downs in the Quaternary climate? Well, these are glacial and interglacial cycles, which we can call ice ages. So technically, an ice age is any time that the Earth has permanent ice on it. So the existence of an Antarctic ice sheet puts us in an ice age. As we saw earlier in carbon dioxide plots of the Phanerozoic, there have been several times where CO2 was too high to have any permanent ice on Earth. But in these ice age times, we go through glacial and interglacial cycles, which are just as they sound. Glacial means that there is a much bigger advance in glacial activity, and then it recedes during interglacials. So this is showing some of that up and down in CO2 over time, and then up to our recent, very rapid global warming and beyond. So in these glacial interglacial cycles, we see that they happen on fairly regular intervals through the Pleistocene and then into our current interglacial, which is called the Holocene. So here I've shown the interglacial to glacial cycles, and you'll see here that the warmer temperatures show interglacials, and then gradually over time you have decreasing temperatures in a glacial to a more rapid interglacial warm-up to then decreasing temperatures gradually over time again, and this cycle repeats itself on fairly predictable intervals. So what is causing these ice ages, these glacial and interglacial cycles on these fairly predictable intervals? It's actually subtle changes in Earth's orbit, these natural Milankovitch cycles. So you'll get a brief introduction of these from me here. Basically, there are three changes that can cause the distribution of sunlight over the Earth to change fairly dramatically and cause these changes in glacial interglacial cycles. The first is the orbit and the shape of the orbit of the Earth. Basically, we can go from a more elliptical to a more circular orbit. The tilt of Earth's axis varies, which determines how much sunlight can reach up to the poles and where that direct sunlight angle is. And then lastly, the wobble of Earth's axis. So think of as a top wobbles. If you spin it and it wobbles eventually, that is what's happening here, and it basically shows which hemisphere is tilted towards and away from the sun during summers and winters. And these three mechanisms happen on fairly predictable timescales over thousands to hundreds of thousands of years, as we can see here with these plots. And the aligning of these three has to do with the ups and downs of the glacial interglacial cycle. So in the US and around the world, these changes in glacials and interglacials have profound impacts that we can see in some of our national parks and areas of the American West. So the Laurentide ice sheet, which covered Michigan during the last glacial maximum, we've learned a little bit about that. So during some of the low times in those Milankovitch cycles, when less sunlight was reaching the northern hemisphere, this Laurentide ice sheet expanded to cover the entirety of Michigan and Indiana, Ohio. Similarly, in the Pleistocene, lakes covered the basin and range. So if the climate changed in the right way. Something like the Great Salt Lake today could have been much, much bigger. And this is where we see a lot of the Bonneville salt flats out in Utah are the evaporated salt deposits from these Lake Bonneville. You can see it's kind of small print, but Lake Bonneville. And we've also had this plot earlier in the class, but in the Sierra Nevada, this is an example of late Pleistocene glaciation in the Sierra Nevada, and this is when parts of Yosemite were carved out from this glaciation. So there are profound impacts on our national parks due to these Pleistocene glacial and interglacial cycles. One of the most important of these cycles was the last glacial maximum. So this was 21,000 years ago. And this is kind of an artistic rendition of where the ice was. You can see some of this, the white is where the glaciers ended. So here you can see it went all the way down past Michigan, and then several mountains were covered in glaciers too. So I'm going to play a short video that shows the melting of the ice sheet since the last glacial maximum, which was the last time that ice was at a maximum, and since then it has only been melting. So here is a video that's showing since 21,000 years ago the ice, simulated ice caps in North America, and now you'll see they are receding further and further until about 7,000 or 6,000 years ago they were essentially in about the same location as they are today, which is just mostly up in Greenland. Okay, so that is what happened as ice receded over the Holocene. So how do we know a lot about the Quaternary? It's closer to us than the Pliocene or the PETM or the Carboniferous. So we have different types of proxies that we can use to tell us about climate that are not only the foraminifera delta 18O or delta 13C. So the first one you may have heard about is an ice core, and this can be a proxy for CO2 and it can be a proxy for temperature. So in the ice in a glacier, as it snows, the air bubbles are actually preserving conditions of the atmosphere. So as it is snowing, the air close to the surface of the ice can get trapped under that snow, and then over thousands and thousands of years, as it continues to snow and build up that glacier, those air bubbles preserve the ancient atmosphere and the concentration of CO2 that was in that ancient atmosphere. So this is a really cool proxy, and it can go back pretty far. An example of one of these from a national park can be found in Denali National Park. So Mount Hunter, you can see this is probably a very good spot for an ice core. There are thick glaciers with hundreds of years of climate records. And my mouse needs to come back. There we go. So in Mount Hunter, several scientists have collected ice cores. And here's a great video that shows scientists collecting records of an ice core in Mount Hunter. I'm going to play it for about a minute. They're up in high altitude environments. The researchers have to live in this snowy valley, and once they collect the ice core, they need to analyze it there, so there's no contamination of their sample. Alright, so you can watch the rest of that video if you want. It's in the lecture slides. So ice cores can only go back as far as the snow and the ancient atmosphere is preserved in those air bubbles, which turns out to be about 800,000 years. So this is a great record for Pleistocene climate, but it doesn't go back to the Pliocene or beyond. So we can really get this glacial interglacial cycle from these ice cores, and on a record like this for CO2, you can see these glacial cycles. My mouse isn't working again. Here we go. You can really see this entire part is collected by an ice core, and just the very last part is what we can get from measurements. So ice cores are a really important proxy for understanding Pleistocene climate. Another great record that you've probably heard about before is the proxy called tree rings. So tree rings can be a proxy for temperature or rainfall. And you probably have heard a little bit about how tree rings work before. Each year, growth of the tree is preserved as a tree ring. So each year, a tree adds another ring to it. And the size and other characteristics of these rings can tell us what the climate was like when that tree was growing. So for a tree ring like you see here, sometimes you have rings that are very close to each other. Other times you have rings that are farther apart. And scientists have very sophisticated ways of understanding how the differences between tree rings actually tell us about warmer or wetter or drier or colder times in climate that impacted how that tree grew. So one great example of tree rings in our national park system is in Great Basin National Park in Nevada, and that is for bristlecone pine trees because these are the oldest living organisms on Earth. So a tree ring from them can show us a very long record of climate with pretty high precision. So these rings can go back about 4,000 years, almost to 5,000 years. So they give us a really great picture of climate over the Holocene. And this is an example. For your reference, Great Basin is in Nevada, in the Basin and Range, and here on the east side. This is a picture of a Great Basin bristlecone pine tree. They look like these really gnarly old trees. They can withstand really harsh weather conditions, but because of that, they grow very slowly and can stay alive for thousands of years. This over here is a record of what a tree ring might show you. This figure is pretty blurry, but it says ring width on the y-axis, which here is a proxy for temperature. So over time, you can see the changes in temperature through the late Holocene, and you can see that last increase in temperature for anthropogenic global warming. So these are really cool records, and because they are the oldest living organisms, they go back further than any other tree ring. So they, as I said, they only go back about as far as 4,000 to 5,000 years. And the tree rings can only show the climate for when the tree was alive, obviously, so we have a great record for the last couple thousand years, but we would need an ice core or something else if we wanted to go further than that. And just as a cool aside, the oldest living tree is a bristlecone pine in the White Mountains of California on the Eastern Sierra. I got a chance to visit this grove a couple years ago, and I highly recommend it if you go on a trip to the Eastern Sierra. So the oldest living tree is there. It's confirmed that it's 4,851 years old, but in the large grove of trees, they do not disclose publicly the exact location and which tree it is, because they do not want anybody going and doing anything stupid to the tree we want to preserve this tree as the oldest living organism. So just an interesting piece of information about these bristlecone pine trees. We can't publicly disclose which one is the oldest one. So then the last proxy that I'm going to talk about for the Quaternary, Pleistocene, and Holocene are what we call speleothems. So speleothems are from caves, and they are a proxy for temperature and rainfall. So what a speleothem actually means is a carbonate mineral deposit from a cave. So it may be from a stalactite or a stalagmite. And the way that they can be used as a proxy for temperature and rainfall is that they actually capture, again, this delta 18O isotopic signal from the rainwater that infiltrates up from the surface through the groundwater and into the cave. There's a lot of complications that happen with these speleothems, and they can be very complicated. So speleothem scientists are very smart, and they can pull apart all of these competing parts of information. But what happens is, as the rainwater percolates down into the cave, there's dissolved calcium carbonate within that rainwater, and then as it reaches the cave, it precipitates out, and over time forms these big stalagmites or stalactites that over thousands of years preserve these calcium carbonate deposits and the isotopes from the rain that tell us differences in temperature or rainfall over time. So one example of a speleothem is in Carlsbad Caverns National Park. So an interesting thing about Carlsbad Caverns, so here you'll see it's on the southeast side of New Mexico. Just across the border is Guadalupe Mountains. So Carlsbad Cavern limestone is in fact Permian in age. So we'll go back to the Permian. Remember, these shallow sea environments would have created this limestone. So that's just kind of a cool connection with the Permian. But the speleothems themselves in Carlsbad Caverns can tell us information about the Quaternary. So this is an example of a speleothem record. I believe it's from Carlsbad Caverns. And it shows you over time these changes in climate over several thousands and hundreds of years. So we can use these speleothem records as proxies for temperature and rainfall. So in a nutshell, the Quaternary period, what I want you to remember is that it shows fluctuations between glacial and interglacial periods. And the current period that we live in is an interglacial period called the Holocene. Okay? So now that we have the Quaternary, I'm going to turn and talk about the present and our future climate, which, as you've seen throughout the course of Phanerozoic climate history, we've been talking in millions to thousands of years. Now we're going to be talking in just under 100 years. So we're at a very different time scale than what we've been talking about before, but because of our current anthropogenic climate change, global warming's rate of warming, we are making really fast changes to the Earth. So you may have learned about this in other courses, but I'm going to give a quick run through of what anthropogenic global warming is. So as I've said, in the Carboniferous and Permian, we have all of these fossil fuel deposits that were formed. And we as humans, as a collective species, are burning these fossil fuels. And when we burn it, we convert it into the CO2 kind of held within it. And that CO2 is going into the Earth's atmosphere and oceans. And by the greenhouse effect, we are warming Earth's climate. So all of this fossil fuel pollution is going to warm Earth's climate. And this is an example of an oil drilling operation in the Permian Basin. You can see the stratigraphy underneath the surface of the Earth down to the Carboniferous and Permian where these oil and gas deposits are. So there's kind of a cool comparison with a national park on how we actually know global warming science and how we know that atmospheric CO2 in the atmosphere is rising. And this is from a famous graph called the Keeling curve. And what the Keeling curve is, I want you to know the name Keeling curve. It is a graph that tracks the atmospheric carbon dioxide from Mauna Loa, Hawaii. So here's where the connection to national park comes in. The 50s or 60s, a guy with the last name of Keeling, he was suspecting that carbon dioxide was going to be rising due to our burning of fossil fuels. So he decided that he wanted to measure carbon dioxide in the atmosphere. Well, carbon dioxide is what's called a well-mixed gas, which means that globally it basically disperses and it should have very similar concentrations around the globe. However, if you are really close to a fossil fuel source, you are going to see that the carbon dioxide concentration is higher than if you were further away. So in order to test pristine air on Earth, Keeling decided that if he went to the top of Mauna Loa, just outside of Hawaii Volcanoes National Park, where an observatory was built, he could measure the pristine air and its carbon dioxide concentration and get a very accurate view of global carbon dioxide concentration. So that is just what he did. And this is an example of the curve started in the late 50s. And you'll see it's atmospheric carbon dioxide. And sure enough, it has been rising ever since. So you'll notice a couple things about the Keeling curve. One, there's this red line. And this red line is the average. So this is not what the measurement is made, but it's actually the average, the running average. And this gray line that goes up and down, fluctuates, kind of looks like those interglacial glacial cycles. These are fluctuations every year in carbon dioxide. So we could call that the annual cycle, the cycle that occurs in 1 year from January up and then down to about October and then up again. So what is the reason for this annual cycle? Well, as you know from biology, carbon dioxide is used by plants for respiration and photosynthesis. And it's important to know that the northern hemisphere, you'll see here I've marked in the red line, has a majority of the land mass and a majority of the plants on Earth. So it paces the carbon dioxide on Earth. So in the winter time, and kind of felt a little bit later, you'll see in the spring, when those plants are respiring, they are releasing carbon dioxide into the atmosphere. So you'll see that the carbon dioxide concentration increases. But then in the summer, when they are absorbing carbon dioxide for photosynthesis, that concentration in the atmosphere dips down. So every year we have this up and down, but because of fossil fuels being emitted into the atmosphere, the signal, the overall trend is going up and up and up. So when we look at carbon dioxide, we can see right from the Permian and Carboniferous delta 13C that anthropogenic global warming is caused by human emissions of CO2. And when we compare our CO2 trend that we saw from the Keeling curve with the global temperature, you can see what we mean by a first order control on climate. So every year, temperature goes up and down and fluctuates due to many different things that I'm not going to get into here. But because CO2 is rising, it is following that same trend. So CO2 is this first order control, whereas all these second order controls may cause these fluctuations around, but the general trend you can see is exactly the same for CO2 and temperature. And again, I showed this before, you can see that in the more negative delta 13C. That's how we know that humans are burning fossil fuels and causing anthropogenic global warming. So anthropogenic global warming is happening, and we know that it has impacts on our national parks. A study came out by a government researcher by the name of Gonzalez, and he showed that national parks are disproportionately affected by global warming. So we need to protect our national parks and adapt them to climate change. This figure shows what he was talking about, and it's a little bit hard to tell. It's a very scientific graph. Scientists love making complicated graphs, but basically these red lines here show a warmer temperature distribution for our national park system than for the average United States. So that means that national parks are experiencing faster warming temperatures than the average land on the United States. So what I want you to know about impacts of global warming on national parks are some of these impacts that national parks are feeling. So first is melting glaciers. And I'll go through a couple of examples in Glacier National Park and Glacier Bay National Park in Alaska. Sea level rise, which I'll show you is happening in Dry Tortugas National Park in Florida. And then drought and wildfires are kind of combined into one category. These drying conditions that can cause fires to start in Lake Mead in Nevada, and a couple of fire examples in Yosemite and Yellowstone. So you've probably seen several of these types of pictures before, but we know that glaciers are melting. And as we've learned from glaciers, melting glaciers means that there is more melting during the summer than accumulation of ice during the winter. So that rate of melting is outpacing the rate of accumulation. And in Glacier Bay here on the left is Muir Glacier, which in 1941 covered this whole U-shaped valley. But in 2004, you can see that this glacier receded, probably that's over a mile, back into this valley here. So big melt from glaciers up in Alaska. And then the same thing in Glacier National Park. This is Grinnell Glacier, which if you have the chance to go to Glacier National Park, I highly recommend hiking up to Grinnell Glacier. It's an absolutely beautiful hike. But you can see that the glacier is receding, and this is in 1981. When I was there about 5 years ago, this glacier was much smaller and had receded much more than it is in this picture. So melting glaciers is one example of an impact of global warming on our national parks. Another is sea level rise, which as this ice on continents is melting, it's adding water to our ocean and raising the sea level. So Dry Tortugas is a really cool national park out at the end of the Florida Keys. You'll see out here. And it is on a very small island with an old 17 or 1800s fort. And you'll notice it is only a couple feet above sea level. So this national park is very vulnerable to sea level rise. Sea level rise of only a couple meters may render this national park, you wouldn't be able to visit it in the same way that you can. There wouldn't really be much land. They may need to build a seawall or just let it become inundated by sea level. So these are figures here on the bottom right that show over some kind of time these projections of how much rising of sea level is going to impact this national park. So you may be visiting it and it will be underwater by the end of the century. The last couple impacts of global warming on our national parks are drought. So Lake Mead, where Hoover Dam is in Nevada, holds the water for Las Vegas. But due to drought over the last several decades, it is actually at 40% capacity in 2019 and has been below full capacity since 1983. So you'll see on this photo these white rocks, and there's a level there. That is kind of the high level, and since then the water has receded. And you'll see it's white because the water is leaching minerals out of the rocks. And that white is kind of like a bathtub ring that shows how far the water has receded in Lake Mead. Drought can also lead to really dry conditions that spark wildfires, and we see these every year in our national parks and our national forests. One of the biggest fires and most famous is in 1988, the fire in Yellowstone, which was the largest wildfire in recorded history in Yellowstone National Park, which affected about 36% of the park. It's a very, very big park, so this has had a very profound impact on Yellowstone National Park. You can see it impacted lots of wildlife, and today if you go to Yellowstone you can see the remnants of the forests that were burned, but it's also really cool because you can see the vegetational succession, which means that a lot of new plants and new life are growing out of these fires. So fires are not necessarily a bad thing, they're a part of our natural ecosystem. But because of our drying and warming world, they're becoming more common and having bigger impacts on these areas. Also, a couple years ago, you may have heard of the Rim Fire in Yosemite in 2013 and 2014. Because of exceptionally strong droughts, this fire actually burned for over a year, and it impacted about 400 square miles, or 250,000, that should be 1,000 acres burned. So this was a very big fire and occurred because of these dry, warm environments, exceptionally warm and dry during this year. If you stood at the tunnel view of Yosemite Valley, this is what you would have seen. You would not have been able to see Half Dome because it was so smoky. This fire was so big you could actually see it from space here. So those are examples of impacts on our national parks. And I just want to end here. Let's see what I'm at time-wise. Great. So I just want to end here talking about how paleoclimate can help us understand where we may be headed with our future global warming. So we've learned a lot about these different time periods and our impacts on our national parks. So this plot, you can see here's 2000. We're somewhere around here. These lines are called RCPs, or representation concentration pathways. Blah. And these are put together by government institutions, and they show the possible future carbon dioxide and temperature regimes based on estimates of how much fossil fuels we will burn. So keep in mind this red line, this is kind of our business as usual, as we call it. So if we continue to burn fossil fuels as we have and do not make any changes, this is called RCP 8.5, and it is a high estimate of how much warming will happen. Other RCPs are these lower parts that if we make changes to our fossil fuel burning, that's where we may take. So I just want to point out that these RCPs, we can look back to paleoclimate to understand where we could be heading if we go down one of them. So RCP 8.5 would be like the PETM. So RCP 8.5 comes all the way up here between 1,000 and 2,000 parts per million of CO2, which projects back to the upper estimates of CO2 during the PETM. Today we're at about 400 parts per million. That's more like a Pliocene climate. So paleoclimate is a really fascinating and important tool that we can use because it helps us understand the climates that we may be heading towards depending on our fossil fuel burning. But it also can help us be optimistic and say, maybe we don't want to go down a path that has crocodiles at the tropics. So we understand that if we continue doing this, that's what will happen. So we can use paleoclimate as a reason and a justification to stop burning fossil fuels. So paleoclimate holds a lot of power in that way. And I just wanted to end with a quote on paleoclimate. The paleoclimate record provides an opportunity to help disparate audiences understand that the Earth has archived its climate history and that this archive is perhaps science's best tool to understand Earth's climate future. So this really shows the importance of paleoclimate in our understanding of Earth's climate future. So that is all I have today. I just want to point out that I put the main points of today's lecture here at the end. So that's a little study guide summary for you. Thanks everyone for listening. I hope you enjoyed it.